Hello everyone, this is Professor Kyung-Hwan. I'm going to give you a makeup class video, and then we'll be looking over problem solution for the exam 2. Okay, let's see. Okay, so we'll be looking at part 2. So we have solved this P90 during the classroom. It is about the angular momentum conservations. Just check. And in this problem, we'll be identify the the situations. The situation is like this. There's a circular platform, and the students is walking from the edges to a certain radius L. Okay, that was the starting point. In this case, you need to find out L is I omega, and then we need to find out L initial is initial final, which is angular momentum conservations. And then what is going to change is that I is changing. I have. And then we need to find out, we know what the II and IF, and then we need to find out omega F. So is I. That was the main theme. Okay. So we have II, and then final IF is here, and then so we have to have II WI is IF WF. And the WF is given by these equations. Okay. So this is local problem we have seen in the classroom. So I will just skip over. This is nothing but the plug-in the numbers for the given locate formula. Okay. And then we have also discussed this one for moment of inertia about the axis is going to be here is the low 1, 2, and then what we need to understand is that this one, this is core, this is shell. And then we need to find out core, moment of inertia for the core, and moment of inertia for the shell, utilizing this case. The shell is given by this one. And then what we need to do is that rearranging this thing, then we have this relationship what we know is that the total I is given by, and then we want to find out what is the radius of a inner core. This is the A. We know total I is, we know what the R is, total radius. And then we have rho 1, rho 2 is given such that A is unknown. Okay, so we can find out what A is following this formula. And this is another case of we have uh, what we need to know is that energy conservation for the rotation, energy conservation for the rotations. So what is happening is a uniform solid disk with a mass 170 kilograms, where there's 4 meters is pivoted around the horizontal axis through its center. A small object of the same mass is glued to the rim of the disk. If the disk is released from the rest with a small object at the end of the horizontal radius, find the angular speed when the small object is directly below the axis. So what is happening here is that the uniform solid disk so 4 meter and 170 kilogram at the horizontal axis, and then it is rotating. Okay. And then if the disk is released from the rest with a small object at the end of the horizontal radius, find the angular speed when the small object is directly below the axis, so that we have a small object here. And then we want to find out this is the initial. This is final. So horizontal axis through the center is perpendicular to disk, is a kind of wheel. Release from the rest with a small object at the end of the horizontal axis, radius, and find out omega when the object is directly below the axis. This is initial and this is the final state. So we need to find out omega. By this small object, it is start rotating. Okay, so what we are going to assume is there is no losses, so mechanical energy is conserved, and the gravitational potential of the uniform disk does not change with the rotation, but its central axis. So that note that this disk is going to rotate, but its position relative to Earth's surface is not going to change. It is rotating around the axis. So that what it means is the gravitational potential, so for instance, mgh, would not change. So what is going to think about, what we have to think about is that, okay, something is rotating, and then we have to think about uh, the conservation of energy. Conservation of energy. So, so initially, every initially here, uh, we can say that because this is the kind of a reference, and then it is initially this mass is here, and then due to the mass is attached, and by the gravitational force or gravitational energy, that the whole thing is going to rotate around this axis. Okay, so like this. So if you look at this disk is just simply rotating. And if you look at this small object, you will find out that its gravitational potential energy is changed. Note that the plate does not have any change in the gravitational energy, but that this small object is changed its position from this rim to this bottom, so that energy, the position difference is given by R. So what we are going to concern is that we have to think about the, here. The point mass drops by R from the horizontal height to the bottom height, so that its potential decrease by mgr. So once again, it was initially here, it's going to rotate, and then here. So potential difference is mgr. And then especially from the initial to final is going to be minus, okay? It's decrease. And the moment of inertia about the axle, this axis is the solid disk is this one. Point mass is mr square. And then total moment of inertia about the axis is given by this one. And then let's say that initially we are going to say that there is no kinetic energy. There is no translation kinetic energy. There is no rotational energy. But in the final state, then we have a both rotational energy given by omega square, and then there is a potential energy difference. But it was initially, we set it at 0, okay? No rotation, so that it's kinetic energy is 0. And if we say it is 0, then it is changed to minus mgr. And then we have to have this energy conservation. And then from this, you get this one, okay? So this problem is strictly about the energy conservations. So basically, energy conservation for rotational kinetic energy plus potential energy. So previous in the translation motion, so we used to have the kinetic energy in the translation motion such that 1/2 mv square plus gravitational potential energy, usually given by mg h. H is the vertical position. But what we are going to solve here is that this one. Rotational energy plus potential energy. Rotational kinetic energy. And then gravitational potential energy. Okay. So this is the, also we have done it during the class, but I'm going to review it. Uh, so in this case, uh, the uniform 11 kilogram bar that is 2.6 long rotates uniformly about a pivot at an end, so that there is a yeah, this rotating about one end. Okay, so L is given, mass is given. Okay, yeah. And rotation rate is a sixth revolution in 3 seconds. So frequency is a 6/3, so 2 revolution for a second. Okay. And then in this case, we need to find out the kinetic energy. Then we do not have any translational motion such that kinetic energy should be I omega scale. So we need to find out I and we need to find out W. So in this case, I is given by this one and omega is given by 2 pi f, okay, in terms of radian per second. Note that this unit is very important, radian per second. And then if you multiply the total formula, which is given by 1/2 I omega square, then you can find out this joule, okay? So we have to have radian per second for the omega is key point here. Okay, so this is also we have done partly during the class, but we have to review once again. The rotating blade of a blender turns with a constant angular acceleration. So it's a rotational kinematics. Zeta is given by zeta 0 omega t. Omega is omega t constant alpha. Alpha is rotational acceleration. And then we have a constant alpha, and then we have 2 alpha. Okay, these are the formula for the rotational. Oh, this is not the V. This is should be omega. Okay, sorry. So this is what it says. Okay. So what we want to find out is that alpha is given and the initial angular speed is given. The final angular speed is given. Okay. And we want to find out number of revolution and during this interval. Okay. So this number of revolution is related with the zeta actually. So utilizing the kinematic, rotational kinematic formula for the constant angular acceleration, we get this one, which is very similar to 2as is given by v square minus v0 square, okay, for translational motion. And then from here, uh, we get the final or initial. And then we get this is given by this one. And then from this setup, from this relationship, so note that WF is given, W0 is given, alpha is given, then we can get the theta. And once you get the theta, theta should be divided by the 2 pi. Note that theta is in terms of radian. So in order to find out the number of revolution, we need to divide theta by 2 pi radian. Then there is one revolution is 360 degree, and which is 2 pi radian. Okay. So we have initially it is the W0 is 0, and then we get this relationship, and then we get this one, and then if we divide by the 2 pi radian, and then we get this relationship. And this is another example of energy conservation. But in this case, we have to think about lows without slipping. Okay, that is the very important case. And the horizontal flow with the velocity. So here that initially it has a translational motion. Okay, translation motion. I'm sorry. It says that the rolls without slipping, and keeps on rolling on the on an angle, and then it stops at the D. Okay. So what we have to consider in this problem is especially rolls without slipping. Then we should be omega. The V is the center of mass translational speed. W is, of course, the rotational speed, angular velocity, angular velocity or speed. Okay, so, and that is the key thing. You know, when we say this, the R is given and V is given, that means from this we note that omega is known. Okay, that's the one thing. And then next thing is that so it goes up to this hill, and then yeah, and then it stops. Then means all the initial energy, both translational and rotational, is going to change into gravitational potential energy. Okay, so initially the potential energy line is potential energy level is 0 compared to this one. So initially it has both translational kinetic energy and the rotational kinetic energy. Okay, and then it should be equal to this final energy. In the final energy, there is no speed, no motion at all. That means there is no kinetic energy. Okay, so initially it has only kinetic energy, and finally it has only potential energy. So we have seen this kind of a problem before. So that all the kinetic energy is changed into potential energy. But the key thing here is that the kinetic energy is now divided into so rotational plus translational. So it has two terms. So it has a translational kinetic energy and rotational kinetic energy. Okay. And then we have to equate this one. And then I is found by these equations. And then you can plug in those numbers. So what is important this problem is that you need to understand the energy conservation first of all. And in this case, it has a kinetic energy only initial phase to the potential energy only in the final case. But the initial kinetic energy has a two contribution. One is the translational motion, and the other one is rotational motion. Okay. Okay, so now let's try to think about a rocket is to be launched from Earth to Mars. When Earth and Mars are aligned along a straight line from the Sun. Okay, so that here's the Sun, and then Earth, and there's a Mars. Okay. When a rocket is to be launched from Earth to Mars, when Earth and Mars are aligned along the straight line like this. If Mars is now 52 degrees ahead of Earth on its orbit around the Sun, okay, when should you launch the rocket? All planet orbit the Sun is the same direction. 1 year on Mars is 1.9 Earth years, and assume circular orbit, even though it is not really. Usually it's a parabolic orbit, but we are going to assume that it is circular. Okay. So what is given is that the Earth year is given by this one, Mars is given by this one. Mars is initially delta zeta 0 is 52 degrees ahead of the Earth. Both move uniformly in the same direction on circular orbit. What is given by year is that the time to take a one revolution. Okay, the time to take a one revolution. That means 2 pi Te and then 2 pi over T Mars can be calculated for angular velocity, right? So that we are going to assume that W is given by this one, W is given by this one. And then alignment occurs when the Earth gains 52 degrees on Mars, such that we get this relationship, okay? And then, so initially it was the 52 degree, and then as it revolves around, and then you need to keep Earth, Mars, Sun, in this case, like this. So the theta angle between the Earth and Moon should become 0. So initially, Mars was this. This is theta 0, okay? And then, I'm sorry, delta theta 0, okay? And then this was the 52 degree, and then we know what the omega is, we know what the Wm is. And then we get this one. Okay. And then we get this one. Note that in this case we get we have to keep the unit all the same. In this case, we keep the degree. Of course, we can change it into the radian, but in this case, we are going to keep it as a degree because we are going to based upon 52 degree. Okay. Of course, we can change the 52 degree in the radian, then we should change the omega E and omega M into radian per second. But note that how we match the unit. So we get the delta theta 0 is given by 52 degree. So we have to keep it. If you want to keep the degree all the time, then WE, WM should be degree per day, degree per day. Okay, so that's the thing. So it's a combination of rotational kinematics. So this is nothing but rotational kinematics. It simply is SF minus SF is equal to VT, something like this. So that we need to understand the problem. If you look at this one in the final phase, it looks very so simple, but you need to find out what has been given and what has to be found out. Okay, so T is unknown. All the other thing is actually given. Okay, so you need to interpret this equation, and then you can get the right one. Another thing is that you have to keep the same dimension for all the parameters. Okay. So Lolo in a printing press turns through an angle theta t given by this one, where gamma is and the beta is. At what value of t does the maximum positive angular velocity occur? So here theta is given, then by the kinematics, omega t is given by d theta dt. Okay. And then what we now need to understand is that maximum positive angular velocity, maximum or minimum, max or minimum over function f is can be found by df fx, let's say. Dx is 0. That's the thing. So let's assume that this is the graph of x versus fx. So in this case, you get df dx is 0, same as here, df dx is 0. So it is the minimum, maximum. So either maximum or minimum, we should have this one. So in this case, what is going to happen here is that, so but in this case, we note that the maximum is occurred, note that it is changing positive slope to negative slope. And this is changing from negative slope to positive slope. So that means it's positive to negative. That means if you take another derivative, then it should be negative. Okay? So the velocity is changing. So the derivative is changing from positive to the negative. So that means if you just plot df or dx, so positive to negative. here. So if you take another derivative, and then it should be negative. Okay. So this is the whole thing. So zeta is given, and then we can find out the angular velocity by directly make a derivative, and then we can find out the extremum, take the derivative of d omega dt equal to 0. And then, but what we need to find out is the maximum, so that in order to get the maximum, we should keep this condition. So let's look at starting from the omega t. If you take the derivative, and then it is given by this one, and then we need to set it to the 0, okay? And then t is this one, or this is the only solution right now. So let's check it is the maximum. If we take a second derivative, this minus 6 beta, that means if beta is positive, it's going to be negative. Okay, so at the t zeta, it is maximum. Okay, so this is the time. And then now let's try to think about 2 point-like particles with the masses m1 and m2 are attached at the ends of the uniform rigid rod. So that and then here is m1, m2. Okay. Rotating in the vertical plane about the frictionless pivot through its center, so that it is the center, and then it's rotating. Okay. And what is the magnitude of angular acceleration of the system when the rod makes an angle set at 2 degrees with the horizontal? So there's vertical, this plane make a 32 angle degree. Okay, so it is very interesting questions here. It is, we have to think about why this is rotating, why this is going to rotate, okay? And the thing is that, so if you go more carefully, let's assume that M1, M2. This is equal distance. And then M2 is giving the gravitational force, and is giving the M1 is also giving the gravitational force. If M1 is much heavier than M2, then there is a difference between these forces, gravitational forces. And then it is going to rotate about this axis, okay? And then the main driving force for this rotation is actually the torque given by these two masses. Okay, so that we need to find out the gravitational torque about the center tau, and the total moment of inertia about the center. And then we need to find out the Newton's third law, tau is given by I alpha. So if we know, first thing we need to find out the moment of inertia, and then secondly we need to find out the tau, and then we can find out angular acceleration by Newton's second law of rotational motion. So the torque, so in this case, the torque is given by this one. So each point mass is at a distance r. Okay, this is L over 2, L over 2. And the lever arms of the weight is, the lever arm over weight is r cosine theta. Okay. Uh, okay, so the distance is given by this one, and then so what we are going to do is that we have to think about torque. Remember that R cross F is given by torque. Okay, so it's not easy to draw here, but anyway, I will try to find out the best way. So here's the gravitational force, and then this is the R, and then angle between these two. It's not easy to draw this one, but so because of its angle, it's not easy. Um, so important thing is that you could have a, remember that there is it's not easy. But anyhow, how do I draw it? Okay, so there is an angle surface here. So here is the mg, and then mg could be defined into this direction and this direction. Okay. So here is the case, and this is the vector. Remember that this vector and how do I? So, okay. Anyway, what is going to happen here is that only the uh, we have a two components in the gravitational force, but I cannot write it here. But it is on the a slanted angle, a slanted plane. Okay, and then the vector R is pointing this way. Okay, this way, and then the only component of the R cross F is going to be this one. Okay, and please have a look at this one. I think that it's a little bit tricky to visualize this because there's a plane, and then all this plane is angled. But anyhow, if you think about this one, then you get tau 1, tau 2, and then the load's own weight is at on the center, so the load torque is 0 because R equal to 0 for this case. And then total torque is given by this one. And then moment of inertia, we should have found out the rod moment of inertia is given by this one. And 2-point mass at the ends is going to be this two things, one at the one end, the other at the other end. And then total in moment of inertia is given by this one. And then we know the tau and then we know the I, so that using the Newton's second law, tau is I alpha, then we can find out what the I is, alpha is, okay? So I will stop here, and then we will resume our discussion in the Wednesday class.